All right, so we talked about the unit step function. Now we need to talk about the unit impulse function, or also known as the delta function. This is a lowercase delta in Greek. And so what the unit impulse function is, it's a really interesting function. For the time being, let's just assume that t is equal to 0 in all these cases. So we're basically just looking at delta of t. Okay, the same way we were looking at u of t over here. So delta of t is a unit impulse, which has two properties, okay? Two very important properties that define it. I'll draw it in blue here. It's basically drawn as just a vertical arrow at whatever value of t that it exists at. So the unit impulse is right at time t equals 0. So right here at 0 in the horizontal axis. And it's basically a function whose value is 0 everywhere before the pulse, 0 everywhere after the pulse. But right at the value of the pulse, right, t equals 0 in this case. Of course, they wrote it as t equals t, but we're letting t be 0 here. Right at the value t equals 0, the value of this pulse is infinity, right? So it goes up to an infinite height at one particular point, okay? And this is a really interesting, seemingly sort of random function to take note of, but it has really useful properties in sampling, in signals, in other parts of EE. And so you'll see more about this in EE360. So this is sort of introductory, and you'll use this a lot in EE360, other signals classes, EE361, and so on. But it's relevant in this context as well because it's very closely related to the unit step function. So we need to study it here as well. So the first property here is that this unit step function basically has a value of 0 everywhere except at the time value t denoted here, which in this case is 0, and that at that time t equals 0, the value is infinite, right? So that's the first property. The second property here states that the area under the curve of this impulse is 1, no matter where that value is. So basically what we're looking at here is if I were to take, I mean, obviously if I have something that looks like this and I want to integrate from 0 to t, this function, let's just call it f of t. If I want to integrate f of t with respect to time, I'm finding the area under that curve, right? That's what I would be doing there. And so what this property is telling us, right, if we integrate from negative infinity all the way to positive infinity, we're basically taking the area under the entire x-axis from negative infinity to plus infinity. And we're going to move along and we're going to have no area anywhere because this function is not defined anywhere. It's 0 everywhere. Sorry, it's defined, but it's 0. And then we get a bump here it's basically instantaneous. It has no width. It exists at one particular instant in time. In this case, it's time t equals 0. And its height is infinite. But we're saying that the area under that infinitely thin but also infinitely tall spike is 1. That's the second property of the unit impulse. It's a really interesting concept, but that's the way that this impulse function is defined. And so, of course, for the unit impulse, we let t go to 0. And so that property would say that the integral from negative infinity to infinity of delta of t is equal to 1. Okay? And of course, we can shift the delta the same way that I said we could shift it here, right? We were showing that we can shift our unit step function by some t. That's what they're doing here, so I'll erase all those zeros now. And basically, instead of existing at time t equals 0, my impulse could exist at time t, or at some other time, okay? And again, if I were to integrate from negative infinity to plus infinity, let's say that this is out of the equation now, I integrate, I get to this t, this little infinite spike at a particular time value t, I take that integral from negative infinity to positive infinity, and I get a value of 1. That is the property of the unit impulse function, okay? And we're going to talk more about this. It'll make more sense in the future videos, but all you have to know for now is that this is a special function called a delta function or a unit impulse function, and it has these two properties. The one property is that it's basically 0 everywhere, except it's infinite at the time value of the pulse. And if you take the integral of one of these pulses, the area under the curve is basically 1. Okay, so for now, we'll leave it right there. I know that this is probably confusing, but just know that this is just a function that we need to define because it has application in electrical engineering. Same with the unit step function, probably a lot less confusing, but this does have application, and you will see that at some point, whether it's in this class or in EE360. All right, so I'm going to end this video here, and we will talk a little bit more about these functions in the next video.